Log on, tune in, find out. Another good idea from Cambridge.
Okay, so I'm going to present some joint work with James Wason, who also works at the MRC Biostatistics Unit. I've tried to talk about something related to design of experiments because of the nature of this workshop. So two-stage clinical trials or two-stage designs are popular because they allow a certain type of flexibility. They allow you to stop the trial early at an initial interim for efficacy or futility. So if there's strong evidence for or against a treatment working, then you can stop the trial prematurely. And these types of trials are good because on average they have a smaller expected sample size than a standard trial without this sort of interim in its stage. So I'm going to consider in this talk a two-stage trial with trying to estimate a binomial proportion parameter, trying to estimate the sort of proportion of patients who respond. So the parameter of interest is P, it's the probability of some endpoint X, the probability that it equals 1. There's no control group in this trial. So the design parameters for a two-stage trial like this are encapsulated in this vector omega. So they're basically the size of the number of patients that you'd have at stage 1 before the interim, the number you'd have at stage 2, and then these other parameters L1, U1 and U2. L1 and U1 tell you if you observe more responses than U1, you should stop for efficacy. So on the y-axis of this plot is the number of responses. If you observe less than L1 responses at stage 1, then you should stop for failure. But if you observe the number of responses within some continuation region, you should continue to collect more data before you make a decision. And the conventional wisdom is to choose the design which minimizes the expected sample size, or maybe some function of the sample size, like a sort of minimax solution maybe. However, this design makes estimation of the response probability a bit harder. Specifically, can induce a bit of bias into the estimate. And the parameter itself might be useful for future study, so planning a further trial if the trial is successful. And various bias-corrected estimates have been proposed. So I'm just going to mention a few of them without going into too many details. So the good thing about working with just the sort of binary case and trying to estimate this a sort of binary response parameter is that you can look at the whole design, the whole design space. I mean the whole parameter space of that parameter. So from 0 to 1, and so for 5 common estimators of this response probability, I can plot the bias in this plot and the mean squared error in a minute. So there are 5 estimators I've got here: the so-called uniform minimum variance unbiased estimator, a median unbiased estimator, the standard maximum likelihood estimator, a bias corrected maximum likelihood estimator, and a conditional UMVUE, which is conditional on the trial reaching the second stage. So for a particular design of where the number of patients overall is 54, the number of patients at stage 1 is 19, and there are those efficacy and futility bounds, I can plot the bias of all of these estimators as a function of P. And I can also plot the mean squared error as well. So for this particular design, the so-called bias corrected maximum likelihood estimator tends to have the smallest mean squared error. So as I said, standard practice is to find a design using a computer that minimizes the expected sample size. But because I care about estimation and bias and things, I thought, why not propose a sort of compromise and try not incorporate the sort of properties of various estimators into design choice. So rather than choosing a design which minimizes the expected sample size, we find a design which minimizes some weighted sum where expected sample size is one component, but bias and mean squared error also plays a role. So bias, mean squared error and mean squared error and expected sample size are given some weight, omega 1 to omega 3. Those weights are positive, and some between 0 and 1 and some to 1. So the expected sample size just depends on the design and the parameter value which you evaluate it at. The mean squared error and the bias depends on the design, the particular estimator out of the 5 that you're using, and also the underlying value of the parameter as well. And to make this thing more well behaved, we scale bias, mean squared error, and expected sample size so that they all lie within the range 0 to 1. And we use this sort of weighted sum to search for optimal design and analysis combinations. So as an example, I consider a two-stage trial where I want a type 1 error of 0.1, and I want 80% power to reject a null hypothesis that the response probability is 0.2 when in fact it's 0.4. So I want to find all admissible design and analysis combinations. I evaluate the expected sample size under the null, but I evaluate the bias and mean squared error under the alternative. So we sort of wrote this computer algorithm and found 10 admissible designs under our admissibility criteria. I've just highlighted 2 cases here. You can see these are the same design, but they're paired with 2 different estimators. And only 2 of the estimators out of the 5 are chosen as being part of admissible design and analysis procedures. So the bias corrected maximum likelihood estimator and the uniform minimum variance unbiased estimator. This is a sort of plot of all of those 10 designs. On the x-axis, I've got the weight that you attribute to bias, omega 1, and on the y-axis, I've got the weight you'd attribute to mean squared error. So you can see design 1, because it occurs when both of those values are 0, that's just the design that minimizes the expected sample size. So that's just the standard design. But design 5 up here is a design which minimizes the mean squared error of the sort of best estimator that you could use. Design 6 and 7 and 9 are fairly good if you want to attribute fairly equal weights of expected sample size, bias, and mean squared error. This is the same plot for the same x and y axis, omega 1 and omega 2, the weights given to bias and mean squared error, and this shows the region which you should tend to use the UMV-UE or the bias corrected MLE. And in general, the bias corrected MLE it should be used if you care more about mean squared error than bias. There's one design 4, which is the exception here, which is the design for these particular parameter values where the UMV-UE had a smaller mean squared error than the bias corrected MLE. So just to summarize, much attention has focused on choosing designs which minimize the expected sample size, and for very good reason, because you're sort of minimizing the number of patients that you need to treat with an experimental treatment in order to show whether it works or not. But efficient designs can lead to estimates with poor properties, and you can trade off small amounts of expected sample size for large bias mean squared error reductions. So potentially you might want to consider near optimal designs which trade off some of those things. So further work, we explored various other ideas. I haven't got time to go into. Have I got time to go? Okay, all right. So different type 1 and type 2 errors, assuming that we're not to evaluate bias and mean squared error over a sort of uniform range rather than a specific value. We also considered trials with stopping for futility only at stage 1, which are generally more common in some sort of medical areas, early stage trials. And also we did some simulations where we evaluated conditional bias and mean squared error, conditional on the trial making it to the second stage. And the rationale for that was saying that you're often in a trial where you stop for a futility only, you probably only care about the estimate going forward if you make it to the second stage of the trial. And so here are some more details about the estimators, but I'll just leave with some references. So thanks very much.
I was a bit surprised that you included bias and mean squared error, because you could, I mean, the mean squared error includes bias.
Yes, yeah, no, that's true. Yeah, so bias comes in twice as sort of a linear and a squared term.
Yeah.
But nevertheless, they are two common measures of estimator performance. But I agree, we're just proposing a sort of general methodology for incorporating estimator performance. So you could have chosen bias and variance, or Pitman closeness and mean squared error, or whatever sort of statistical summaries you think are important in terms of estimation. But I agree, I take your point that bias comes in twice.
Okay, let's thank Jack again.